So same thing in 2 dimensions and 3 dimensions. You could have 3 possibilities in 2 dimensions. The lines are parallel and they never intersect. The lines have different slopes. Obviously, they're going to intersect once. And they're the exact same line. They're intersecting all the time. That's in 2 dimensions. In 3 dimensions, we add something called skew lines. They're not parallel, but they never intersect. It's really like there's lots of lines that can be not parallel, going in completely different directions, but never intersect in 3 dimensions. And so those are called skew lines. And they're very important for airplanes that they fly on those paths and never intersect with each other. And we'll also find out with airplanes, it's okay if the pathways of 2 airplanes intersect as long as it's not at the same time. Because if it's at the same time, then that is disastrous. But I'm sure there's lots of planes that are at the same place as another plane was 5 days ago, and that's okay. So here is a 2-dimensional question, and we can take that 2-dimensional question I always like my vector equations written with the column vectors. Ooh, do you know what this Greek letter is? Lambda. That's like one of my favorite Greek letters to write.
Why?
I don't know, it just, why? It looks like an upside down Y. Maybe that's why.
That's what I was saying.
So are these lines ones that intersect only once, or are these lines ones that intersect many times? Are the same line? Well, if we set up our parametric equations and we equate them together, we will always get a system of equations, 2 equations with 2 unknowns, which you now have so many ways you could solve it. You could use matrices if you wanted to. You could use Gaussian elimination or Gaussian-Jordan elimination, or you could just use plain old substitution from grade 10 to solve this. I'm going to use elimination. So I multiplied equation 2 by 2, so my lambda is eliminated. So much for me liking lambda. And I get t is equal to -5. Once I found out t is equal to -5, I can find out lambda is equal to 4. And since there is one solution to this, these 2 lines are concurrent. So R1, I would write it like this, 3, 4 plus S to -1. And R2, I think I wrote it in, yeah, I did write that. And R2 is -9, 10 plus T times -6, 3. So we're going to find out that some of these questions are going to use 2 different parameters, one S, one T, one lambda, one T. And then we're going to work in real life questions. And then in real life questions, there's only one parameter, T, and T stands for time. But for these questions, are these exactly the same line? Well, if we go to solve the parametric equations, or if we look at the direction vectors, can you see that these are parallel? That the slope of this one would be -1/2, the slope of this one would be -3/6. -3/6 reduces to -1/2. So if the slopes are the same, you have two possibilities. Either they're exactly the same line, or they're parallel and they would never intersect. Okay? This question is asking if they're exactly the same line, if they're coincident. So do they have a common point? Because if they have a point in common and they're going in the same direction, they have to be exactly the same line. And we obviously know that 3, 4 is on R1, because it was told to us initially in the question. So that means, is 3, 4 also on R2? And if we plug 3, 4 into R2, if we find a nice value of t that works, then it's on the line. If we can't find a nice value of t that works, then it's not on the line. And we can check this with the parametric equations. Look at the first one. It says t is equal to -2. We look on the second one. T is still equal to -2. So that tells us that 3, 4 is on that other line as well. And since they go in the same direction, and they share a point, they must be the same line. So a very common question is like the next one. We go to 3 dimensions, and we ask in 3 dimensions, do these two lines intersect? Do they cross? And if they cross, where do they cross? So the way we do this is we look at the parametric equations for each one. The x-coordinate on R1, and the x-coordinate on R2. The y-coordinate on R1, the y-coordinate on R2. And each of these, when you equate them, will make a system of equations. And what's interesting about the system of equations is that you would technically get 3 equations with 3 unknowns. Like I'm going to do it here in purple. I could add a third one if I equated the z coordinates. I equate the x coordinates, I get one equation. I equate the y coordinates, I get a second equation. I equate the z coordinates, I get a third equation. When you have 2 things that you don't know, how many equations do you need to solve? You only need 2 of them. So if I took equation 1 and equation 2, I could figure out that s should be 0. From getting s equals 0, I could plug that in into either one of those equations, and I could figure out that t has to be equal to 1. But just because you figured out what s is and what t is in those first 2, there's still a possibility these lines could be skewed. Like they appear to intersect when you look at, if you're looking straight at me and I put my arms like this, it appears that there's a crossing point. I'm going to tell you that's not true. My arms are not going through each other and stuck and glued together. That would be probably quite painful, right? They appear from one direction, but you have to still check, does it work in the third equation as well? So I check equation 3. Oh. And when I plug in S is 0 and T is 1, it doesn't come out to be true. So that tells us these lines are skewed. If it ended up being true, then you could take either S equals 0 or T equals 1 and plug it into the original equation. Like if S is 0, my point is 3, 0, and negative 1. If T is 1, my point would be 3, 0, and 1. See how the first two worked out? Because that's what we used. We used equation 1 and equation 2, and we solved, and we're like, oh, it's working. But we had to check equation 3, and that third point doesn't work. And it would have to work in all three of them in order for those points to intersect and for you to find an answer. So this can be a little bit tricky because you think you found the answer, but if you don't check, you might not realize that they're skewed. And so now we can take these three-dimensional vectors, two-dimensional vectors, and apply them to real-life speed, time, and velocity questions. Okay? So here's our vector equation of our line, where r is a vector, a is a vector, and b is a vector. R is a position vector, so we have some sort of position for an airplane, a boat, a car. We have a specific place that it's at, and we have the direction that plane or boat or car is going. And for the most part, this is pretty realistic because, especially when you're looking on a small scale, vehicles are traveling in a straight line. Our direction vector, we call our velocity vector. Because we're going to use time, and so if your direction vector was 3, 4, that would mean in 1 unit of time, you would go 3 in the x direction, 4 up. In other words, you would have traveled 5 units, because if you did a squared plus b squared equals c squared, you would have traveled 5 units in a certain direction. So that becomes your velocity vector because it has a direction and its length is its speed. Okay. So here is an object moving in 2 dimensions. It starts at 1, -1. And how do we call this a starting point? Because when time is 0, that's where it would be. It starts at 1, -1. It is going 3 to the right and 4 up. So it has a speed of 5 kilometers per hour because it looks like the vectors are measured in kilometers and time is measured in hours. Write down the velocity vector. So our velocity vector is 3, 4. Its length is 5. So its speed is 5 kilometers per hour. Describe its motion in words. Okay? The object starts at 1, -1 and moves in a direction of 3, 4 at a speed of 5 kilometers per hour. How do we take our vector equation and change it to a Cartesian form? Well, we could start with our parametric equations. Solve for t, because in the Cartesian form there's no time, right? It's just an equation. So if we solve for t and equate them, we get the Cartesian form. And now we just have to rearrange until we get it into the form that they like. So I multiply both sides by 4, both sides by 3. Put my numbers on one side, my x and my y on the other side. Oh, and for these questions, there is a theme. It is your job to figure out by the end of class what the theme of today's lesson is. Adding intrigue. Okay, question number 1. We have a moving object is described by the parametric equation x equals 4 plus 5t and y equals 5 minus 2t. This is in 2 dimensions, so this could, a really good place to represent 2 dimensions is boats on water, because they're pretty flat. You don't have to worry about the z dimension. Or cars driving in the prairies. Pretty flat. Don't have to worry about elevation changes. They give us the parametric equations. Could you write the vector equations? Oh, and then I would move arrows over the I and the J. So here's our vector equation. Write down the velocity vector. Well, the velocity vector is your direction vector. And the length of it would be a squared plus b squared equals c squared. 5 squared is 25, negative 2 squared is 4. 25 and 4 is 29. All right. What kind of object are we, what moving object are we talking about? Maybe it is a pet hamster. And it happens to only run in straight lines. And your pet hamster is running. And you see that there's a pole located at the point 39, negative 9. Will your hamster run into that pole? That is the question. So what we do is we set up our vector equation line and we plug in the point. If there exists a t that makes this happen, our poor hamster will run into this pole. So we look at parametric equation 1, parametric equation 2. We solve equation 1, t is 7. We solve equation 2, t is 7. If only the hamster had been looking, the object hits the pole. With a set. All right, example 2. We have a jet flying at a speed of 700 kilometers in the direction of 2, 6, negative 3. What is the velocity vector? So the velocity vector would have that direction, but the velocity vector would need a length of 700. And currently, if I figure out the length of this one, it's not going to be 700. Its length, if we do a squared plus b squared plus c squared, is just 7. What could I possibly do to make its length 700? Multiply by 100. And sometimes, if this wasn't a nice number that you could do this easily, you could find the unit vector, which is the length of 1, right? If I put the 1/7 in front of this, that would be the unit vector. And then I could times that by 700. But since it's such easy math to go from here, you can easily see you need to multiply by 100. So there's my unit vector. I can multiply that unit vector by 700, which is the same as taking that original vector and multiplying it by 100. It's in the same direction, but now has a length of 700. Two more examples. Yes?
Why did we typically multiply by 100 or you wrote multiply by 700?
Well, I multiplied the unit vector. Let's add an L here just
Oh,
for,
I got it.
right?
Yeah.
Multiply. Multiplied the unit vector by 700. But I couldn't just multiply the actual vector because it had a length of 7 and the mental math was easy by 100. A yacht leaves a harbor and its position x comma y relative to the harbor is given by the vector equation xy equals t 5 8. A cargo ship at the time t is given by xy equals 6 3 plus t 3 7. Find the speed of the yacht. So in order to find the speed, we need its direction vector or its velocity vector. Its velocity vector is 5 8. So its speed is just its length, 89 kilometers per hour. I changed it on yours, but when I originally had this, I don't know where I got this question from. They had changed the language in the second one from the yacht to becoming a pleasure boat. So find the distance of the cargo ship from the harbor when the yacht starts its journey. Question.
Is the theme crashes?
Well, I'm not giving away the theme yet. So the cargo ship here at time 0 would be at 6 3. And the yacht at time 0 is at the origin, which is the harbor. What's the distance between those two? Well, that's just the length of 6 3. So we could do a squared plus b squared. They are the square root of 45 kilometers apart at time 0. Which is quite a fair distance, right? That's almost 7 kilometers apart. If both the yacht and the cargo ship continued on this straight line, after what period would they collide? Question, go up again. I can go up. How far do you move? Right there? Yes. Okay. So try to solve that on your own. It's T.
No, what if I copied that? Where'd you get it?
Would they collide? Well, oh yes, they do. 3 hours. They are not going very fast. Like, there's the cargo. And this is on an ocean, right? There's not much to see on an ocean other than other boats. So you can imagine the crew going, look, there's the cargo ship. Look, it's getting closer. And 3 hours later, boom. And our last question. Also 2 dimensions. We could do a 3-dimensional one too, but we have vectors, 1 kilometer east, 1 kilometer north. Here we have a circle with a radius of 25, with the center being at the origin. And that's where a lighthouse is. And the lighthouse, you can see the light in that circle. So a ship, eventually 31 kilometers west and 32 kilometers south, so somewhere here, right, is moving parallel to the vector 4 3 with a speed of 20 kilometers per hour. After leaving P, the ship is at 25. So we're going to write down the vector OP There's our starting point, negative 31, negative 32. And if we wanted to create the equation of this ship, we have our starting point. Why is the direction vector 1612? We know the direction it's heading in. It told us that was 4-3. But why is it 1612? Well, it needed to have a speed of 20. And in the direction 4-3, that has a length of 5. So can you see that if you needed a length of 20, you could multiply by 4. The math is easy. Or you could get the unit vector and then multiply by 20. So here's my unit vector. If I multiply that by 20, I get my velocity vector has to be 1612. Same direction, but now its length is 20. So our vector equation line, all points on the path, we have our starting vector and our velocity vector, and therefore that equation does make sense. So it started at P, and in 1 hour it gets to R. So we could find O to R by just plugging in 1 for T and get negative 15, negative 20. And then figuring out PR, well, PR would just be R minus P, because again, if you're ever forgetting that formula, right? Once you have OP and OR, if you wanted to get from P to R, you could first go negative O to P, which is negative P, and then go from O to R. So visualizing it, I often visualize negative P plus R. Mathematically, it's easier just to write R minus P. And does it make sense that if you took the 2 and subtracted, you get 1612? Because that's what you traveled. That was your velocity vector. Show that when the ship reaches R, the lighthouse first becomes visible. Well, we know that R is negative 1520. The lighthouse at 0, 0. If we figure out the length or the magnitude of OR, it is exactly 25 kilometers. And we were told that the radius of the lighthouse was 25. And we're about to get to part E, which will further the theme of today's lesson. A second ship's path can be described. Will the boats collide? And here this should be T again. But even without that, if we set up our parametric equations and we solve them, there is a solution. Now, if this was a real life question, the variable T should be the same in both. Because then you're like, this is just showing that their pathways cross. But we're using a variable T and a variable S, it could be that they cross at a different time. If we had the same variable in both of them, then we would show that they would in fact collide. But we can find the point at 33:16. And if that time was the same, they'll collide at a time of 4 hours. So sad.